All right, so hello everyone and welcome to MakeLearn 360. So in this question, I would solve you know, it's actually a question about Coulombic friction. Okay, so there are two main kind of friction. We have the viscous damping, and then we have Coulombic damping. So this one is about Coulomb or dry friction. Okay, so let's read the problem together and solve it. So you realize that for viscous damping, the force is proportional to so you have something called like CS dot, but this one is not like that. This one is actually dry friction or Coulombic friction, so it's not the same. All right, so we have a simple system where the mass is given by 7 kg, and then we have got a stiffness K of 1.2 kilonewton per meter, and then this is experiencing some Coulombic friction of constant magnitude, which is equal to what? 1 Newton. So the frictional force due to the dry friction is 1 Newton. And then it's giving an initial displacement of 80 mm. Okay, so that's sort of the initial displacement, which is 80 mm from the mid position. That's the position for which the spring exerts no force. So determine from first principles the time which will elapse for motion to cease and the displacement from the mid position at that time. So essentially, you have to calculate the sort of time. You've got a spring mass system which is using some form of Coulombic damping, and then it will kind of experience this. So you give it a slight displacement. Okay, as soon as you give it a slight displacement, it is going to vibrate. And now we are saying that as it vibrates, we should calculate the time at which this vibration will cease, and then the displacement at that point where the vibration will cease. Okay, right. So with this question, let me first of all calculate the natural frequency, which is the most important parameter of the vibration. So one, we want to calculate the natural frequency. So natural frequency, right? And this natural frequency is nothing but omega n given by square root of k divided by m. So even if you can't solve this question, at least the first thing that you should be able to do is the natural frequency. So it's given by the square root of 1200, which is the same as 1.2 kilonewton divided by 7. So essentially the natural frequency of this system is so let's pick our calculators and do it together. It's going to be square root of what? 1200 divided by 7. And that's going to give us 13.09 radian per second. So 13.09 radian per second. So this is actually the natural frequency for you. So that is it. And then the second aspect of the question is that after calculating the natural frequency, in fact, there is going to be, because of the dry friction, there is going to be constant frictional energy per half cycle. Okay, there is going to be constant frictional energy per half cycle. So this is how we are going to write that. So if there is going to be constant energy, so constant energy loss, okay, because of the Coulombic friction, there is going to be constant energy loss due to friction per half cycle. You don't need to write this. I'm just writing it for you to understand. Okay, but then how do you calculate this sort of energy? First of all, you have to calculate the amplitude, and that amplitude is what will be decreasing. So there is always that kind of amplitude reduction, and it is given by change in SC, which is actually given by 2 FC divided by K, where K is the stiffness. So FC is the Coulombic force, and then sorry, so that is it. I think this is actually about Coulombic friction. So this is actually coming from Coulombic friction. If you don't understand Coulombic friction, you cannot be able to solve this, because this is not the same as the normal viscous damping. Okay, so is going to be, so 2 multiplied by the magnitude of the Coulombic friction, which is 1, divided by 1200. So we've got 2 into 1 into 1200. That's essentially so 1.667 millimeters. So this is kind of the amplitude reduction. Okay, so this is kind of the amplitude reduction per cycle. So amplitude reduction per cycle, or per half cycle. Let me put it that way. Now, so it means that it will be decreasing in the Coulombic damping. The amplitude will be decreasing linearly in each half cycle, and that is the peak amplitude. Now the next step is we have to calculate the number of half cycle until rest. Okay, so if you are beginning with, let's say, an x0 value, which is 80 mm, then to calculate the number of half cycle until it finally comes to rest, this is simply given by so n will be given by the first one, which is 0.080 meters, millimeters, meters. Then I divide this, which is actually the same as the displacement. Okay, and then I'll divide this by the per amplitude. Okay, so 0. Or let me just say 1.667 times 10 minus 3. So why are we doing this? We are doing this because we want to calculate what we call the number of half cycles, because that is what we are going to use to calculate the time it will take for it to come to rest after the motion is set in. Okay, so that is 1.667 times 10 to the power minus 3. And so yeah, so we have 47.99, which is somewhere approximately 48 cycles. So this 48 cycles here is actually half cycles. Okay, half cycles until rest. So half cycles until rest. Okay, so that's what it means, that it will be doing this until it finally comes to rest. 48 half cycles. That's basically what we are trying to say. Now, what is the time per half cycle? So the time per half cycle is the same as the period, because if it does this, the time that it will take to complete each half cycle, which is the period, is going to be 2 pi divided by omega n. Okay, which is what? So the time is going to be 2 pi divided by 13.09. Okay, and this is going to be what? So we have 2 pi, and then we divide this by 13.09. That's essentially somewhere 0.5. Okay, so essentially we have, or let's say, yeah, okay, 0.48 seconds is okay. 0.48 seconds. 0.48 seconds. So this is actually the period that, and this period is going to be the undamped natural period. Okay, so if we are interested in the half cycle, then for a half cycle, for T half, that's period of half cycle. So period of half cycle is going to be the number of half cycles that we have. In this case, for half cycle, we will divide it by 2, or 1/2 the period it will take for the full. Okay, which is going to be 0.24 seconds. So after getting this 0.24 seconds, then you now say that, okay, if the half cycle is 0.2, then for 48, what will be the time? Okay, because we know that the 48 half cycle is the number that it will take till it comes to rest, the number of cycles. So for 48 half cycles, T will be what? N. So N times T half. Okay, and that is going to be 48 half cycles multiplied by the time each half cycle will go, which is 0.24. And if you're able to calculate this, this will be the time that it will take, because you have 48 half cycles. So one half cycle, another half cycle, the other half cycle. If you do 48 half cycle, it comes to rest. So the time that you calculate will be the time that it will come to rest. I hope it makes sense. So we are using the half cycle approach, and this is coming from Coulombic friction. This is different from viscous damping. Okay, so I think maybe you are not familiar with this, but this is not viscous damping, right? So 11.52 seconds is the time that it will take, very quick, the time that it take to come to stop. It means that it will be doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to 48, and then after 11.52 seconds it's come to stop. But then what is the displacement at that point in time? So to calculate the displacement at that point in time is you are going to use the formula, which is final displacement, so time to stop. This is time to rest. Okay, time to rest. So to get the final displacement, the formula is given by xf equals x naught minus n minus 1 multiplied by change in displacement, which is given by 0.080 minus 48 minus 1 multiplied by 1.667 times 10 minus 3. Okay, and this will give us the kind of the final displacement. Okay, so actually the final displacement will be sorry about that. So if we calculate it, we get what? So we have 0.080 minus 48 minus 1, and this will multiply 1.667 times 10 raised to the power minus 3, and then that is it. So essentially this is going to be 1.65 millimeters. Okay, so that is it. In fact, so this is displacement at rest. Displacement at stop. Okay, when it come, or rest. Okay, so at rest or stop. So when it finally come to stop, or when it finally come to rest, that will be the displacement. Right, so this question has been solved. Thank you very much for watching.